G'day again, welcome back to Mathematics 302. Hope you're having a good morning or a good evening, as the case may be. Just move my image out of the way. This is week 8. Got a lot to get through this week, so we're going to have 3 sets of recordings. This is part A. So in part A, we're going to do the limit of functions, accumulation points, convergence, and continuous functions. I'm going to do a lot more on convergence in part B, which is a review of a bit of first year. But I'll just mention it here. I think it's important to mention it. So we'll just do these 4. So let's get on with it. Okay, limit of function. If we consider the following functions, which you've almost certainly seen before. So y equals 2x. In the lower, there's no limit. In the upper, there's no limit. So y equals 2x has no limit. So when we're looking at limits, we're considering obviously the y value up and down, not the x values. So y equals e to the x, and we'll know what that looks like. So the lower, the bound is 0, and the upper has got no limit and just curves up forever. x1 y equals ln x, so you should know that if you get a line and you draw not y equals 2x, but y equals x right through there, y equals ln x is the mirror image. Hopefully you recall that. The lower, there is no limit. It goes down forever. The upper, there is no limit either. That goes up forever. My image is going to be in the way of the last picture. So we've got y equals cos x, which again you will have seen. So the upper is 1, the lower is -1, and it just goes up and down forever and ever in both directions. So that has an upper limit and a lower limit. So important to notice here, no limits, no limit upper, no limits again, and this has got an upper and a lower. All right, so even though this ln x doesn't cross over here, we're looking at the limits in terms of y values. Okay, next point. Get back down there. Okay, in set theory, we look at these 1, 2, 2, 4, 3, 6, where we've got b equals 2a. There is no limit. It goes on forever. We'll get 1, 1, 2, 4, 3, 9, where b equals a squared. Again, there is no limit. What is the limit of the sets of the set A, where you've got A1, A2, A3, up to AN? And here, there are no limits here. I was talking about, I mean, you can go backwards as well, but there is no limit. What is the limit of the set A, where you're going A1, A2, A3, all the way up to AN, so indefinitely? It's pretty impossible to tell what it is. You don't know whether it's A1, AN, you don't know what shape that is, because it's not possible to tell what that is without more information. So if we give some more information, well, maybe we give you this. Then you'll be able to tell what a limit is. Obviously, we'd have to have some values here so you can see what's going on. Or we could do this. And obviously, again, we'd have to have values here and here so you can see what's going on. Or we can do this. And again, you'd have to have values here and here to see what's going on, because you can't really tell from this information what is the limit of this set when it's just, they're not actual integer values. Okay, so what we want is a limit which a set converges to when we're getting a limit of the functions, and that occurs when lim_inf and lim_sup are equal. So the infimum and the supremum are equal. So lower limit, upper limit. So if we look at that, there's a reference there, which you can look at it in the notes if you want to. That's on LibreText, which I find pretty useful. Good revision for you. An accumulation point, a limit point, a cluster point, is a point which has points in the neighborhood within a given set, though the accumulation point may not actually be in the set. So this means that a point can be arbitrarily approximated by other points within the set, even if the accumulation point itself is not in the set. Now, I'm not going to go through a proof of that. I'm just going to give you examples, fairly simple examples of accumulation points. So here we go. Here is a set 1, 2, 3, 1, 2, 3, 1, 2, 3, and it just keeps going. So this sequence has 3 accumulation or limit points, 1, 2, and 3, which are pretty obvious. So these points will occur infinitely many times. So what we want to look at, what is lim_sup? the supremum, it's 3. Obviously, that is the biggest value you can get. And lim inf, the lowest value you can get, is 1. So now, because lim sup is not equal to lim inf as n approaches infinity, it does not converge. Okay, so it's pretty easy to master that. If lim sup does not equal the limit of infimum, then it's not going to converge. Example 2. So we've got an equals e to the minus n, where n is greater than or equal, sorry, just greater than 1. So the infimum is 0, which is obvious. The supremum is 1 over e. Again, that is obvious. But if we consider the limit of inf and sup as n goes to infinity, what happens? Lim sup becomes 0 and lim inf becomes 0 as well. So as it approaches infinity, as n approaches infinity, the supremum and the infimum both go to 0. It gets smaller, smaller, smaller. So this converges to 0. Okay, so just because you figure it out and you go, oh, this is not going to converge because I can see it here, as it approaches infinity, they do converge. So just saying that on convergence. Convergence can also occur in a power series, which you may have seen before in first year. You may not have, but you may have. We have a radius of convergence or an interval of convergence. So, for example, if you had this power series, the thing to look for is that the center is going to be 2. I'm going to go more through a lot more examples of this in part B. So this is just sort of to warm up for you. get you looking at power series again. So this is or for the first time if you haven't seen them. So the sum here from 0 to infinity of an, and we've got x plus 4 to the n. So the center is going to be minus 4. And if we look at this one, we've got x to the n over n factorial. What you're looking at is here, and you're wanting this to go to 0. So the center here is going to be 0. Put 0 on top, the whole thing's 0. So that's just things to pay attention to or just to be aware of and get your appetite whet for part B. Okay, continuous functions, which is the last point we'll make in this part of the lecture. To prove a function is continuous at a point, show that the function exists at some point c. So you've got fc. The limit of the function at c exists and is the same from both sides. The value of the function at c, fc, is the same as the limit. So you want to show those 3 things. So let's do some examples. So if we just show it on the graph. So here you've got a, and fa is undefined. Here you've got a split function, so it includes a, but it doesn't include it there. So the lim of fa does not exist. And here you've got the lim of fa does not equal the lim of fx. So that's a problem as well. So these would be your 3 problems where it's not continuous. So let's look at that in real life with real numbers. So determine whether the function x squared minus 4 over x minus 2 is continuous at x equals 2. And I've just drawn a random graph there. So we've got x minus 4, x squared minus 4 over x minus 2 is continuous at x equals 2. So what do? You can see it fairly obviously if you put in 2. First attempt to calculate f2. So that will be your first move. Make sure the value actually exists. So if we put in 2, we put in a 2 there and a 2 there. 2 squared minus 4 over 2 minus 2. It's undefined since we can't divide by 0. So therefore, it is not continuous. Pretty easy. Next one. Determine whether the function fx equals minus x squared plus 4 and 4x minus 8. So we've got this one for x less than or equal to 3, and this one for x greater than 3. Is it continuous at x equals 3? Again, first step, put in 3. So if we put in 3, which is in this section here, so put in 3, minus 3 squared is 9 plus 4, minus 9 plus 4 is minus 5. So that exists. Yay, first step, that's good. So now we're going to calculate a limit as x approaches 3 from above and below. So we know we've got a limit there of 5 as it approaches 3. And from below, we're going to the other section where it's approaching 3. It's not quite equaling 3. We get to 4. And so we've got 4 and minus 5. I've just rewritten the minus 5 there again. So therefore, it's not a continuous function because they don't approach the same number from above and below. So this will be, sorry, this is above and this is below. My apologies. So from below is this and from above is this. Okay, another one. Determine whether the function fx equals sine x over x for x not equal to 0 and 1, should have moved that one across here, for x equals 0 is continuous at x equals 0. So again, let's put in 0 and f0 is 1. Well, that's helpful. And the limit of fx equals the limit of sine x over x as x approaches 0, and they're both 1, so that's helpful. So f0, and if you put in f0, which equals 1, that equals the limit as x approaches 0 of fx, so therefore it's continuous. So that one is, the other two aren't. So there we go. Okay, that's all for this one. Stay safe until I see you again shortly. And God bless you. Okay, bye. Whoop, clicked on the wrong thing.